Okay, good almost afternoon, people. Assalamu alaikum. Welcome back to Inspired Teens Grade 12 Physics/Chemistry. Where in today's lesson, we'll be doing electricity/electric circuit, same thing, right? So, sorry for the delay, by the way, slightly, but we're going to be starting now. Okay. Yes, electricity. Okay, let's switch our brain from acids and bases to electricity. Let us discuss Ohm's law. Okay, so Ohm's law states that the potential difference across a conductor is directly proportional, okay, to the current in that conductor at a constant temperature. Okay, and Ohm's law gives us, 1 second. Okay, and Ohm's law gives us the following equation. Okay, V is equal to I times R, okay, where V is voltage measured in volts and I is current measured in amps, in amps, okay, and R is resistance measured in ohms, and that's the symbol for an ohm, okay. It also, according to this formula, okay, gives us the relationship between current and resistance, okay, provided that voltage remains the same. So, okay, so it gives us a relationship where current is indirectly proportional to resistance. So if we have V is equal to I times R, we have this mathematical equation, okay, and let's say that the voltage remains constant. So if the voltage remains constant, right, we can even use numbers to test it out. Let's just say my voltage is, let's use a bigger number, 20. Let's use a nice number, 30. Okay, so if I have 5 amps of current, okay, how much resistance is required to have 30 volts? That's easy. We just do multiplication or division. That would be 6. 6 ohms would be needed. Now remember, we're keeping our voltage the same, all right? We're keeping our voltage the same, okay? And let us increase our current and see what happens to our resistance. If I increase my current to 10, the resistance would have to decrease. It would have to decrease to what? To 3. Okay, so while the voltage remains constant, okay, we can see this inverse relationship between current and resistance. That when you would increase your current, okay, it would decrease your resistance. Okay, and also if we had gone from 5 to, let's do what? Let's decrease our current to 2. What effect would that have on the resistance? It would have to increase to 15. So if we decrease one, the other increases, and so on. Okay, inverse proportion. If you increase one, the other has to decrease. If you decrease one, the other increases. Okay, so that's what Ohm's law gives us, this relationship between current and resistance as well. Right? Okay, that I is inversely proportional to resistance, right? And that's something very important that we'll see later on as well. Okay, now let's just discuss some formulas, okay, as well as some definitions, or these are actually definitions, and then the formulas that have given us those definitions. So voltage is equal to W over Q, okay? This is work, this is coulombs or charge, okay, and we refer to this as the defining formula because it gives us the definition. Okay, voltage can be defined as the amount of energy delivered per coulomb, energy delivered or work done per coulomb, okay, per charge essentially. Then we have I, okay, which is current, and it's Q over delta T, the charge divided by the change in time, and anything that has delta T in the denominator we refer to as rate of change, okay, and this is rate of change of charge essentially, or just rate of charge flowing, rate of change of the charge, rate of charge flowing, same difference. Okay, so that's the definition and the formula that gives us that definition, right? And Also, like charge can be, it's not as often, but charge can be calculated by saying Q over delta T, and voltage can be calculated by saying W over Q. Okay, let's have a look at power, right? So power is equal to W over delta T. This is the rate of energy delivered, or the rate of change of work done, or the rate of change of energy delivered, etc. Now, power also has other formulas, okay, because remember, if we rearrange these in different ways, okay, we can also get a power formula as V times I, V squared over R, or I squared times R. Okay, so these are all formulas for power. W over delta T, V times I, V squared over R, I squared times R. These are all given in the formula sheet, okay? And you'll see when we happen to do a power question, we'll come back to that and discuss it. It's for power, it's generally simple. You want to look at the formula sheet and see which equation you can use according to which variables you have, okay? But we'll get to that, as well as this, the cost we'll discuss, but it's just there for now. Now, let's just again, one more time, just go over our V is equal to I times R, which is our formula that comes from Ohm's law, okay? And this formula has V, which again is volts. Oh, sorry, V is, which is voltage measured in volts. A, which is current, sorry, I, which is current, which is measured in amps. And this omega symbol for resistance, and it's measured in ohms. Okay. Another thing to note is voltage is measured by a voltmeter, okay, which is always connected in parallel, okay, and current is always measured with an ammeter, okay, which is always connected in series. Okay, so just other important things to note. Now, what is the difference between parallel and what is the difference between series? That's what we're going to go over next. Okay, so firstly, a key thing that's written immediately on top is that series is referred to as what? Series is referred to as a voltage divider, and parallel is referred to as a current divider. Now, those that you need to memorize. Okay, just for the sake of memorizing, just know it before anything, before even thinking. Like a parrot, tell yourself, what is series? A voltage divider. What is current? What is parallel? Current divider. And if you want to remember, like PCSV, I don't know, something like that, get creative. Okay, but series is a voltage divider, parallel is a current divider. Just know that before you even know the understanding of it, memorize that like a parrot. Okay, so that when the time comes to apply that concept, you know it in your head already without even thinking. Okay, now we're going to we'll discuss why we refer to series as a voltage divider and current as a, series as a voltage divider and parallel as a current divider. Now, first thing we can note is the difference in the connection between a series circuit and a parallel circuit. So the difference is in the connection of the resistors. So we have one resistor. Okay, let's go through the things first. Here we have a cell, okay, which supplies the volts. Here we have the conducting wire. This line all across is the conducting wire. Here we have an ammeter, which measures the current. Here we have a resistor. Okay, then we have the same things here, right? We have, okay, the only thing we don't have yet is a voltmeter, but we'll have it in another diagram. We'll go through it, okay? We have a cell, a resistor, and another resistor. So you can see now the difference in connection. Here they are all connected on a straight line, okay? One resistor leads to the next resistor, leads to the next one, leads to the next one. While in parallel, okay, what happens is there's a splitting of the circuit, okay? So it's not in a straight line. We'll discuss that better in a bit, okay? It's this, it's not connected in a straight line, okay? In a series of straight lines, okay? It's connected with parallel lines, okay? Parallel wires. And the main thing we'll discuss again is that the current will split, okay? Now, another key thing to note, current, okay, always travels from where to where? Always travels from positive to negative. Current always travels from positive to negative. That's important to note. And the positive terminal is the big terminal. always, okay? So current basically always travels from the big terminal to the small terminal. So if you always see me start there, you know why? Because current travels from the big terminal to the small terminal, or from the positive terminal to the negative terminal, okay? That's the other thing. Now, okay, now let us discuss anything we're missing. No. Now let us discuss the differences between the two. Very important. In series, we can calculate the total resistance. So we have 1, 2, 3 resistors. We can calculate the total resistance by simply adding them up. So we can just say R1 plus R2 plus R3. R1 plus R2 plus R3. This gives us the total resistance. But the same cannot be said about parallel. So if you want to calculate the total resistance here, you'd actually have to use a calculation 1 over, in fact, we'll change that to RT. Let's do this. Let's do this, R total. Obviously, in this case, there's only parallel and series. So we're just going to call this R series. The reason for that is, yes, it is R total in this specific diagram because there's only series in the circuit. Okay, but now in other examples, you'll be dealing with series and parallel in one circuit. So the same applies with this. I'm just going to call it R parallel, even though for their respective circuits, okay, they are the total resistance. So R parallel can be calculated with the following formula. R1 over R parallel, actually. 1 over R parallel is equal to, okay, so let's get rid of this. We don't need it. 1 over R parallel is equal to 1 over R1 plus 1 over R2 plus however many resistors we need to add. Okay, 3, 4, generally 2 or 3 at most. Okay, so 1 over Rp is equal to 1 over R1 plus 1 over R2 plus 1 over R3. And then when you calculate this, okay, you're actually going to have to flip it. You're going to have to invert it because the answer of this is giving you the value of 1 over Rp, not Rp itself. So you're going to have to invert it, right? When we do the example, we'll go through it properly. Now, what's next? We're going to discuss current. So important, okay? Resistance in series to calculate the total what's the word? Equivalent resistance, okay? Just meaning the total resistance that all of this adds up to, okay? You would just add them up in series. However, in parallel, there's a specific formula that any resistor connected in parallel, you would have to use that formula. 1 over Rp is equal to 1 over R1 plus 1 over R2, etc. Now let us discuss what? Let us discuss current. Now, the current in the series, in series, is always equal to the total current. Always, always, always. The current in series is always equal to the total current. So any ammeter that's connected to a series part of the circuit, okay, you'll see when we do two different things, you'll understand better. Any ammeter connected to the series part of the circuit always reads I total. This specific one especially, it reads I as well, sorry. This one reads I total because it's connected in series, okay? If I had to put an ammeter here, this would not register or not read I total because it's on a parallel branch, okay? It's on a parallel part of the circuit, okay? So note the difference. Any ammeter connected to the series part of the circuit would definitely always give you I total, but on a parallel branch, you're not getting I total. And the other thing is that every single resistor that's connected in a series part, the series part of the circuit, they all use the same current. And what current is that? I total. They all use the same current. Okay, so essentially what happens, right? Let us discuss it. It's a nice time to discuss this. It's a perfect time to discuss this. Current starts from the positive and travels through and goes through R1, then through R2, R through, then to R3, So it goes through R1, goes through R2, goes to R3, and eventually goes back into the battery. Okay, so the current travels along one single path. Okay, you can think of it like water. It's blue right now. Okay, it travels through one single path, and that is the reason why every connector in every resistor in series uses I total, uses all of the current. Current does not split in series. It carries on as one full current. But, however, let us look at the circuit of parallel. Okay, now the current starts at the positive terminal and travels and travels and travels until it gets here. When it gets here, it is now faced with an option. Okay, it's faced with an option. It can either go left or it can either go down. And current, okay, it goes both ways. So the current goes down, okay, and the current goes left. Okay, and what happens is, so let's do it in like two different shades of blue so we can. Sorry. Okay, so the current would go down. Okay. All right. And the current would also go left. Okay, so it would split into two different currents. And then thereafter, it would rejoin once again. Okay, so the current would split at this point. Okay, and it would rejoin at this point here. Okay, and I'll give you an example in terms of numbers, right? Let's say that I total for this circuit is 5 amps. Okay, so actually what goes into here is a total of 5 amps. Okay, but then thereafter it splits. So maybe down 2 amps will go. Okay, and left in this circuit 3 amps will go. Okay, so current splits. In a parallel circuit, current splits. Current, you can think of it like water again. The water would go left, it would have two options, and it would go down. Water would go both ways, and then they'd rejoin at that point there. So what leaves, one more time, what leaves is a full 5 amps. So what went into the parallel branch was 5 amps, the total current, by the way. Okay, however it split, it actually splits in proportion, okay, depending on the resistance. Okay, so for example, 2 goes down, 3 goes left. Okay, they rejoin once again when the parallel circuit ends to form 5 amps. Okay, let's just go through one more. This is just an example. Obviously, these numbers may not be exact. They really depend on the resistance. Okay, how do we determine? Okay, we'll go through that later. But for now, we need to know that current splits. Okay, so we'll draw that one for now. But in this case, to calculate I total, the I total splits up into two different branches. So you'd have to say I branch 1 plus I branch 2, however many branches they are. Okay, mainly just 2 branches. Okay, so this is what we would call I branch 1. And we'd call this I branch 2. Okay, let's pink them out. Okay, so the current splits into 2 different branches of current. Okay, and the total would be the sum of both of them. Right, the sum of both of them, 3 plus 2 in this specific case, 3 plus 2 gives us 5. Okay, so that's how we can get I total, right? Just note that if we had to have an ammeter here, on the other hand, okay, this is actually, if you don't understand it now, it's fine, we'll go through it later. This would actually read I total, because it's on the series part of the circuit. This one doesn't read I total because it's on the parallel part, but this is actually the series part. we'll discuss what exactly is the series part and how to determine it in a bit. But this would read I total of 5, right? There is an I total that exists in this, but then it splits in the parallel branch 3 and 2. So this actually doesn't read 2. This would read what? This one would actually read 3. Okay. And if we had to put 1 here, it would read 2 on that specific branch. Okay, that's important to keep in note. So just by the way, let's complete this. The current in series circuit is equal to the total current. It's equal to the current that goes through resistor 1. It's equal to the current that goes through resistor 2. It's equal to the current that goes through resistor 3, and so on if there's more resistors. So this is the case in series. Okay, in parallel, they split. That's why I can represent it by adding them up. Okay, let's discuss the final thing, and that is voltage. Okay, now the thing here is in parallel, in series, what splits is, so current may flow through like water. So current may flow through, and I total would be present everywhere. All the resistors would use I total, but what splits in series is voltage. Voltage split. So let's just say this has 50 volts. Comes from our battery. In a series circuit, that voltage splits, right? Maybe 20 volts go here. Okay. 10 volts, maybe 15, 20. Maybe 15 volts go there. And 20 volts go there. No. 10 volts. That's 35 and 15. Yeah. 20 volts go there. And then that's 35. And then it's another 15. What numbers did I have that are different? 12, whatever. Let's just say 12 volts go here. Okay. And that would make this last one 18. No, that's 18, I think. 23. Yeah, 23. Okay, so that would make this last one 23. Whatever. These numbers are arbitrary values, meaning they're not specific, they're not exact, right? Not that they're not exact, but it doesn't matter what these values are. But the key thing is we understand that voltage definitely splits in a series circuit, and it's shared in proportion. It splits in proportion, doesn't split equally. It doesn't split randomly. Okay, it splits according to how much resistance is in each resistor. Okay, and actually, the higher the resistance, okay, the lower the voltage that it gets. The higher the resistance, the lower the voltage that it gets. Okay. However, so in series, voltage may split. However, in parallel, voltage does not split. So let's just say the volts here are given as 50 volts. Okay, 50 volts in this battery. This guy would use 50 volts, and this guy would use 50 volts. Okay, so the volts don't split. However many volts goes into the parallel circuit, both resistors would use that same amount of volts. Okay, so for series, the voltage in series can be calculated by adding, or let's just say in this case, V total, can be calculated by adding the volts, indicating to us that the voltage in series splits, but in parallel, the voltage in parallel is equal to each voltage. So in this case, we can even say, to be more accurate, voltage in parallel is equal to the voltage on the first branch, and it's equal to the voltage on the second branch, etc. And in this case, if we wanted to be more accurate, we can say that the voltage in a series circuit is equal to the first voltage resistor, the second voltage resistor, and the third voltage resistor, and any other resistor. Sorry, no, we needed to add them. It's equal to them all added up, any resistor calculated in any resistor in series, we would add them up. We would add the voltage of any resistor in series, and we would get the total volt in a series circuit. Okay, so going back to this here, very important. Like I said, you need to know this. You need to just by heart it, and now we have the understanding, right? Series divides voltage while parallel divides current. And that will help you to remember, if series divides voltage, that means that its current remains the same. And if parallel divides current, that means that its voltage remains the same. Okay, so you memorize series as a voltage divider and parallel as a current divider. That's the important thing. Okay, and here we understand all these concepts. Okay, how to calculate resistance in series compared to parallel, current in series compared to parallel, voltage in series compared to parallel, and yeah. Okay, so I hope that made sense. Let's see, is there anything else? No, but just one or two concepts to discuss here. Let's compare a cell and a battery. So when we just have one positive and negative terminal, this is referred to as one singular cell. When we have multiple cells joined together, this is when we create a battery. So just to understand the difference between a cell and a battery. Cell is just one of these, and a battery is multiple of them. Okay, then we move on. We're going to look at this diagram now. Okay, so I want to actually just spend some time going through a few diagrams. So we'll go through this diagram and maybe another one or another two. I just want us to understand what? I want us to understand just having a look at and distinguishing circuits with parallel and series connections and understanding where the series and the parallel is in a given circuit. Now, here we have here we have a battery. So it looks like a cell, but this entire dot line, we'll just refer to it as a battery because I'll add more actually. Battery or cell, depending on how many they are. Obviously, here there's just one, so this is technically a cell. Okay, so let's just do that actually, be more specific. This is a cell or a battery, depending on how many you are given. Okay, and this dotted line actually represents the battery, right? And this here, very important, introduced in grade 12, okay, which we're going to discuss. This guy is internal resistance. This is not ideal. This is internal resistance. This represents internal resistance. Okay, and we'll discuss what's that in a bit. This represents what? This represents a switch. Okay, this represents a resistor. This is an ammeter, of course, connected in parallel. Okay, now let us try and identify our parallel and our series. So I have a really simple way of doing it. Okay, a simple way to distinguish where's your parallel part of your branch, where's your series. You always want to start, you can use your finger or a highlighter, at the positive terminal of the battery, and you start flowing your current. Okay, so the current starts flowing, it goes down, it goes down, it goes down, it goes down, and eventually until it gets there. Now, the current was flowing cool and easy the whole time until it reached that point, right? At this point here, now it has a choice, okay? Now it can either go up or down, so now it has to decide. And whenever you find that your current eventually reaches some sort of T junction, it doesn't have to specifically be a T junction, but it reaches a point where it has two options. It can either go up or it can go down. This is now the part of your circuit that is parallel. As soon as you reach the part where your current has two options, those two options are the parallel parts of the circuit. Okay, so the entire, this blue highlighted portion, that is all in series. These are all still series. Okay, all of the blue highlighted part is still in series. Now, what's going to be highlighted in red? This is now the parallel branch. So we have the first branch, and then we have the second branch. Okay, and we have the second branch. And yes, they do meet up okay, and they meet up again, okay. They meet up at that point. So the two different branches end and they become one branch again. And what are we back on? We're back on series. This is now again, once more, series until it goes back to the negative terminal. Okay, so what's in blue is the series part of the circuit. Okay, the series part of the circuit. It is also known as the main branch. Okay, that's important. The series is also known as the main branch. So when we refer to what is the main branch, it's anything that's on the series circuit. So that's how we distinguish between the series part of the graph and the parallel part of the graph. Start with your finger at the positive terminal, okay? And follow the current, go with the current, go with the current, go with the current until when? Until you realize the current now has to split. Once it splits into two branches, those two branches are the parallel branches of the circuit, and they're the parallel part of the circuit. So there there's this one, we've identified the series and also the parallel. This is the parallel branch. So this is series circuit and parallel combined in one. Now let's have a look at another diagram quickly. And let's see if we can identify where's the parallel and where's the series. So let's just say this one is not given, but let's just say that's a positive terminal, that's a negative terminal. Okay, this represents the battery as well. Okay, and we start at the positive and we go down. Okay, and we have to stop there. Why do we have to stop there? Because now we have two options. As soon as we have two options, we should know, okay, I'm in the parallel part of my branch. So the two options, one that goes there, okay, and another one that goes there. Those are the two options that the current has. So the current will split. Okay, it will split and it will rejoin, however, for the rest of the branch. And now we continue again. We see if we can continue. As soon as we get to a stop where it wants us to split, that's parallel, but it doesn't. We don't get to that point, and the entire rest of the graph remains in series. So whatever is in blue is in series, whatever is in red is in parallel. Okay, what about this? This might look confusing, but follow the same concept. Positive terminal, negative terminal. Start with your finger, start at the positive terminal and follow the current. Follow the current. Now, if I get here, I see that it already has an option. Okay, but don't worry, we ignore voltmeters. Voltmeters, we don't have to consider it, right? It's not going to steal the current. Okay, so what happens is we can skip over the voltmeter, but we continue, and then we reach here, and then we're like, shucks, we have two options. So this point here, at this point, it's already now going to be what? It's going to split into the parallel branch because now it has two options. It can either go down, or it can either go left, actually. Okay, or it can go down. Okay, and you'll see it has two branches, right? Let's do that. Two branches, and it regroups again. They rejoin again once more to form the series part of the graph again. Okay, so whatever is in red is in parallel, whatever is in blue is in series, right? Ignore voltmeters and ammeters. Okay, so that's a neat little trick. Just follow it from the positive and don't get confused. However the diagram is however it is. If it's upside down, inwards, it's confusing, connected, started, positive terminal. As soon as you get to a split, okay, that's my parallel branches. Okay, and it's also the same thing, right? On the entire series, sorry, we have I total. So the total current, I total. The entire blue portion is I total until it needs to split. What splits? Parallel is a current divider. So now it splits into I branch 1 and I branch 2. Okay, as soon as we reach parallel, that's when it splits into I branch 1, I branch 2, I branch 1, I branch 2 the whole way. I branch 1, I branch 1, okay, I branch 2. This is the current, I branch 2, until they rejoin once more to form what? I total again. I total leaves the parallel circuit. I total enters the parallel circuit. Okay, yes, it then splits as it splits, okay, into I branch 1, I branch 2. Sorry. Okay, but then it rejoins again to form I total, and along the entire series part of the circuit, we have I total, I total, I total, all the way, every part of the series. That's why whenever you put an ammeter in the series part of the circuit, it will always read I total. Okay, because on the series part of the circuit, there's always I total. But if I had to put a, what do you call it, an ammeter here, what is it going to read? It's going to read I branch 1, whatever I branch 1's current is. If I put an ammeter here, what is it going to read? It's going to read I branch 2's current, whatever I branch 2's current is. Okay, so just keep that in mind. Muy importante, very important, understanding the difference. Okay, let's do a little stuff for this. So the switch, by the way, the switch here is closed. How could it be open? It would be flipped upwards like this, and there'd be a hole in the circuit. There'd be a hole in the circuit that looks like that. Okay, that would mean that the switch is open, and as you can see, current travels and goes here, and it's like, wait, I can't go anywhere else. So the current circuit's not like working properly. There's no current in the circuit if the switch is open. If the switch is closed, it allows for the current to continue to flow. Okay, so anything else? Okay, let's do an example, right? What we also have here, however, you'll notice, okay, let's look at the two different branches. Okay, we have this branch starts here and ends there. Okay, then we also have this branch here, starts here, ends there. Okay, I hope you can see those two different branches. Let's maybe do this. And that. Okay, maybe that helps a little bit. But we have two of those branches, the I branch 1, the upper branch, and the lower branch. Now let's have a look at the resistors on that branch. Now, the resistors on that branch, on I branch 2, okay, I branch 2, we have 3 ohm resistor. Okay, in I branch 1, sorry, this is 1, this is 2. In I branch 1, we have the 2 ohm resistor and the 4 ohm resistor. Okay, so we actually have 2 resistors. On one single parallel branch, we have 2 resistors. Now, what you need to notice is on this parallel branch, even though this is the green, this is the red parallel part of the circuit. However, on this parallel branch, we have 2 resistors, and how are they connected? They are connected in series. Okay, if you can see that they are continuous, right? There's no split to go to 1 ohm and to go to one resistor and the other resistor. They are drawn continuously. The wire leads directly from the 2 ohm resistor into the 4 ohm resistor. So within this parallel branch, okay, so we have series branch, parallel branch, and within the parallel branch, we have a series connection. Okay, so let's talk about resistance calculation. Now, parallel resistance is calculated by saying 1 over Rp is equal to 1 over R1 in this case plus 1 over R2, because there's just 2 of them. Now, this would be equal to 1 over, if we consider 1 over R2, I branch 2 just has 1 3 ohm resistor. So that would just be over 3. That's 3 ohm resistor there. But now, what about, how do we get the total of this? Because it's connected in series, right? How do you calculate the total resistance in series? You just simply add them up. There's no need to do 1 over R1, 1 over R2. So the mistake that some people might make is they might say 1 over 2 plus 1 over 4 plus 1 over 3 for this one, because like, oh no, it's all in parallel. That is incorrect, because On the one parallel branch, yes, we do have 3. Okay. And on the other parallel branch, we need to find the total resistance of the branch. That's what fits into the formula, the total resistance of the branch. And since that branch has a series connection, the total resistance of this branch could be calculated by saying R total for that specific branch, R branch is equal to R1 plus R2 plus R3, etc., because it's connected in series. So therefore, we would say in this case, because there's a series on a parallel, okay, we would say 1 over, and how do you calculate the resistance in series? By simply adding them. So it becomes 1 over, and we add 2 plus 4 plus 1 over 3. So this is 1 over 6 plus 1 over 3. This is equal to 1 over RP. Now you can do the calculation. In your calculator, you just say 1 over 6 plus 1 over 1 over 6 plus 1 over 3. Here you get 1 over RP as 1 over 2. So now if you want to flip this and make it RP over 1, you'd have to flip this one as well and make it 2 over 1. So therefore, parallel branches resistance is equal to 2 ohms. Okay, so what's the key takeaway here? The first one we went through. The second one is this thing here, right? RP, how do you calculate it? You flip it at the end. Okay, and then the first one we went through is understanding a series on a parallel. Okay, so this is part of a parallel branch. This entire red portion is part of a parallel branch. However, on it, we have what? 2 resistors which are connected in series with one another. So to get the effective or the total resistance of that specific branch, we would just add them, like how we would add regular series. Okay, this would differ compared to, how would I compare this to an all parallel circuit? If I just had to draw a quick sketch, okay, you could have had okay, you could have had it like this instead, where you had 1 resistor here, 1 resistor there, 1 resistor there. All right, and this was, let's just say, the 3 ohm resistor, this was the 2 ohm resistor, and this was the 4 ohm resistor. In this case, they are all connected in parallel. So therefore, this could simply be 1 over 3 plus 1 over 2, 1 over RP. Because they are all in parallel with one another. But in this case, not all of them are in parallel to one another. 2 and 4 are series. So we can get the total of that branch by adding them in series. And then the 2 and the 4 are in parallel to the 3. So we say 1 over 6 plus 1 over 3 is equal to 1 over RP. Okay, if you wanted to get 1 over 3 plus 1 over 2 plus 1 over 4, this is what the configuration would have to look like. Okay, the entire thing, meaning all of them have to be in parallel. Let's move this. Okay, cool. Okay, that's it for now. Let us end it there. I'm going to leave the lesson open for the next few minutes. If anyone has any questions, please feel free to ask. Please do use this time to ask any questions. If you want me to clarify anything or you have any questions for physics in general, please use this time to ask these questions. The seminar thing will be open for the next 5 to 10 minutes, depending on how many questions we have. Thank you. Did you hear my response? Sorry, I'm not sure if you could hear me. No, oh, sorry, I was muted, I didn't realize. I was saying that, yeah, okay, so I'll answer your question first. Yes, this will be the topic next week. We'll continue from here, okay? And then we also currently busy with assets and bases during the other lesson. But yeah, let me just repeat what I was saying previously to this question as well. I said next week we'll continue with this, okay? Discuss voltmeter around the battery, parallel connections, some calculations with regards to just discussing important stuff. You'll see the total current is very important in calculations. We'll do some basic questions before moving on to some more complicated questions, as well as graphs as well, experiments, which we will discuss in this section. So quite a long section. So yeah. When were we doing VPM? VPM, I'm pretty sure we've done already. So if you go to the YouTube playlist, you should find the videos on vertical projectile motion and the notes in the Google Drive. F1. Okay, but if there are no further questions, let us end it there then. Okay, thank you guys so much for joining. I hope you guys have a good week of school, and I will see you guys next week. Okay, Jazakallah khair. Assalamu alaikum.